All right, so we are in section 2.2 now. We're talking about what are called separable equations. This is actually going to be the first section that we talk about in the book that goes over a method for solving a differential equation. So far we've looked at differential equations and their solutions and how to take a family of functions or a specific function and show that it's a solution to a differential equation. But we haven't talked yet about how to come up with that family of solutions if we're not given it explicitly. So that's what a lot of this class is methods for finding solutions to differential equations. And this is the most natural starting point, separable equations. So before we talk about that, let's talk about the absolute simplest case for a differential equation. What is the easiest type of differential equation to solve? And that's any dE that takes this form. dy dx equals a function of just x. The reason for that is because using the fundamental theorem of calculus, if this is just a function of x, I can solve this just by taking an integral of both sides. Okay, so let's do an example to show why that's the case. I want to solve this dE right here. So that what I'm going to do is integrate dy dx with respect to x. Okay, and that means I would be taking the integral with respect to x on the right-hand side as well, ln of x over x dx. Okay, now on this side, remember y is a function of x and I have its derivative here, and by the fundamental theorem of calculus, the integral of this derivative should just be the function y itself. Now normally, yes, I would say y plus c. I'm not going to write the plus c here, and I'm going to explain why in just a moment. Over on this side, I need to integrate the natural log of x over x, and this is a very straightforward u substitution. I would set u equal to the natural log of x, which implies that du would equal 1 over x dx, and that means that this integral can be instead written this way. It's the same thing as the integral of u du. U du, it has an integral of 1/2 u squared plus c. Okay, and then substituting my natural log of x in for the u there, I'm going to get this 1/2 natural log of x, absolute value of x technically, plus c. Squared, sorry, I needed to square that. Square. Okay, now, excuse me. This is my solution. Why did I not put a plus c on this side? Well, remember, c is that constant of integration, and it's an arbitrary constant, meaning it just represents any constant we might want to put there. If I put, for example, a plus c over here, first of all, I have to call these different things, maybe plus c1 on this side and plus c2 on this side. But that means I have an arbitrary constant that I'm adding over here and another arbitrary constant that I'm adding over here. If I were to subtract the constant from the left-hand side over to the right-hand side, it would just combine with that arbitrary constant and become another arbitrary constant. Okay, so something that's going to happen a lot in this class is that this constant of integration, we have to keep in mind that it's arbitrary. It's not a specific value unless we have an IVP and we're solving for it somehow. So as we're solving these differential equations and we use integrals in different ways to do that, we're going to kind of play fast and loose with that constant of integration a lot. And I'll kind of explain as we do those sorts of examples, why we're justified in doing that. But we may do some things that initially don't seem right, and they are justified. So anyways, that little disclaimer out of the way. This is the simplest type of differential equation to solve. And again, it's just because after integrating both sides, because this is just a function of x, we can integrate it with respect to x and get a solution. Now, the overwhelming majority of differential equations we encounter in this class will not be of that type, and that's because there's not much going on there. So what is the next step up in difficulty then, if that's the easiest kind of differential equation to solve? And the answer would be what we're talking about in this section, separable equations. So let's talk about those next. Okay, We have a definition. So a first order differential equation is called separable if it can be written in this form. dy dx equals a function of x times a function of y. Okay, so to give a few examples and a few non-examples, these three differential equations here are all separable. So for example here, x squared times cosine of y equals dy dx. Notice on the right hand side, it's a function of x times a function of y. Over here, dx dt, x is the function, t is the independent variable, equals x over t. It looks like it's a function of x divided by a function of y, but notice, a function of x divided by a function of t, because those are the two variables I'm using. But you can think of this as x times 1 over t. So it does have this form to it. This guy right here, dp dt equals 5e to the p plus t. If you were to rewrite this as 5e to the p times e to the t, you can see that this is actually a function of p times a function of t. So it's a product of the functions. It's a product of functions of each variable, and that's what makes that separable. These three examples down here are not separable. dy dx equals x plus y. This is a sum, not a product. dA dt equals the natural log of TA. So even though I'm multiplying these two, I'm then taking a natural log. So it's not just a product of these two functions, or these two variables. And no matter how you try to manipulate this, you can't turn it in to a product of a function of x, or sorry, a function of t times a function of a. Similarly, this guy right here, dt, capital T and lowercase t being the two variables, equals 2 capital T to the power of lowercase t. This cannot be represented as a product of functions of uppercase t and lowercase t. So those are non-separable, or just not separable DEs. Okay. We're going to talk through the solution method for solving a separable DE, and then we're going to do some examples. So let's begin by supposing that we want to solve just a general separable DE, and what I'm going to do is change the form that it appears in. So I'm going to take my function of y here, h of y, and define a new function p of y to be its reciprocal. And the reason I'm doing that is because I want to start by dividing both sides of this equation by h of y. But dividing both sides by h of y is the same thing as multiplying by the reciprocal of h of y, or multiplying by p of y. So multiplying both sides by p of y here gives me this. P of y dy dx equals g of x. Now, I want to make note of something on this left-hand side here. If I were to change the notation that I'm using, first of all, we understand that y is actually a function of x, right? That's the only reason we're able to talk about dy dx in the first place. So I can use function notation and represent y as y of x. In addition to that, dy dx, if I wanted to, I could rewrite that as y prime of x. Okay, and the right-hand side is still g of x. But putting it in this form might make it look a little bit more familiar. What this looks like to me is almost, it almost looks like something we would, a function that we have taken the derivative of and applied the chain rule to. Okay, not exactly, because that's not a derivative out here, but let's just kind of run with that idea. So I would like to solve for y somehow. Remember, that's what we're doing when we're solving a separable, or solving any differential equation. We're trying to find a representation of the function y. Because these involve derivatives, I anticipate needing to undo that somehow, and an integral is how we would normally do that. So I'm going to integrate, take an indefinite integral of both sides. Okay, now looking at the left-hand side and kind of thinking through the fact that this kind of resembled the chain rule. The chain rule from Calculus 1 is what justifies U substitution when we learn about U substitution and taking integrals. So coming down here, after doing this, setting up this integral on this left-hand side, it makes sense to set this up, make a variable substitution, y of x. Now I'm just going to say y equals y of x instead of calling it u, because I'd like to keep things in terms of x's and y's if I can. So if I make the variable substitution y equals y of x, then what would dy be? Well, dy would be the derivative of this, y prime of x, and then we pick up a dx factor right here. So that shows up right here. That means I can rewrite this left-hand side as p of y dy, which we're seeing right here. This right-hand side, I still haven't really done anything aside from integrate that g of x function. Okay? Now, I want to point something out about this. If we go back up to this step, okay, if I were to treat this dy dx as a fraction, okay, so meaning I can clear denominators and things like that, and if I were to multiply both sides of this equation by dx, notice that I would end up with this, p of y dy equals g of x dx. Okay, notice that these are the integrands that are showing up down here. So instead of going through this work, this is the justification for what we're doing. What we really want to think of doing is separating anything with separating the variables by taking anything with a y and putting it on one side, including the dy. Anything with an x, including the dx, putting that on the other side. I have separated the variables here, all y's on the left, all x's on the right. And then I can integrate both sides, which is what's happening down here, and use that to solve for y in later steps. So again, these are called separable equations. These are the types of equations we can do this with, and this method is called separation of variables. So let's take a look at some examples now. I want to begin by solving this differential equation. dy dx plus 2xy squared equals 0. Right now it doesn't appear to take the form of a separable equation, but if I subtracted that second term over, notice I have dy dx equals negative 2xy squared. Now I can see that it is in fact a separable equation because I have a dy dx equals a function of x times a function of y. Next thing I'm going to do is separate my variables. So I'm going to try and get anything with an x in it over to the right. That means that I need to multiply both sides by dx to get that dx over here. I also need to divide both sides by y squared to move this y squared to the left-hand side. That gives me this. dy over y squared equals negative 2x dx. Okay? That I've separated the variables. Y is on one side, x is on the other. And now I can do that last step in the previous page, which is integrate both sides. On this left-hand side, we're going to have the indefinite integral of dy over y squared equals the indefinite integral of negative 2x dx. Both of these are easy integrals to evaluate. On my left-hand side, this is equal to negative 1 over y. And again, I would normally write plus c here. But as we saw in the first example, if you integrate two sides of an equation, you only need to bother with one constant of integration. It's redundant to put two because we can always combine them. Okay. On this left-hand side, the integral of negative 2x dx, so the antiderivative, is going to be negative x squared. And here's where I'm going to put that plus c. Okay. Now, next thing I'm going to do, let's go like this. I'm going to multiply both sides by negative 1, so I get 1 over y equals positive x squared. Now look at this, plus c. Now wait, you say, why didn't you change that into a minus c? Shouldn't that negative 1 that you multiplied both sides have turned that into a minus? Technically, yes, but it doesn't matter. Right? Because what is that really doing? I had an arbitrary constant here, and by multiplying both sides by negative 1, that arbitrary constant is still an arbitrary constant. It's still just another constant that we don't know the value of, and it doesn't really make a difference if I have this as a plus or a minus here. So it's not going to make a difference if I have a plus or a minus here. It doesn't actually need to change. Okay? That's what I mean by playing fast and loose with that constant of integration. There are some times where we do have to be kind of careful with that, but in this case, it's not going to matter if I change the sign there. Okay. Now I have 1 over y on this side. The goal here is to solve for y explicitly if we can, so I'm going to take reciprocals of both sides. Y equals 1 over x squared plus c. What we have here is a family of solutions to our differential equation. Okay, and if I want to, I can check this. It's a good idea if you're unsure that you have the correct solution to a differential equation to check it the way that we talked about in chapter 1. This will in fact work though. It's a one parameter family of solutions because I have a single parameter c that I can plug any real number into and it'll always produce solutions to that original dE up there. Okay? So that's one example in the bag. We have 3 more examples we're going to work through to finish out this section. Okay, and here's our next one. I want to solve dy dx equals y squared minus 1 over x squared minus 1. And notice I have an initial condition here as well. Y of 2 equals 2. So this is an IVP, which means I don't just want an infinite family of solutions. I want to obtain a single solution. Now we still approach this the same way. We just have more work to do than we did in the previous problem. So working again with separation of variables, hopefully you can see why this is a separable equation. Make sure that you're convinced that that's the case before going any further. But now I can separate my x's and my y's. I will end up with this, dy over y squared minus 1 equals dx over x squared minus 1. Okay? And we know that the goal here is to integrate both sides. After separating my variables, I want to set up those integrals. Now notice, first of all, the U substitution is not going to work here. This is a classic partial fractions example. It's a very easy partial fractions example, but if you haven't done partial fractions in a while, hopefully this example gets you, brushed up on that. So another thing I notice is that except for the change in the label of my variable, the integral on the left side looks identical to the one on the right-hand side. So that means if I want to evaluate this integral using partial fractions, I can go through that whole process and do it. I don't need to redo all that work for the right-hand side. The partial fractions will give me a solution for both sides. I just need to remember that this one is in terms of y, while that's in terms of x. So let's start on this guy. Dy over y squared minus 1. We would like to factor both sides here. So I'm going to get dy over y plus 1, y minus 1 equals the integral of dx over x plus 1, x minus 1. Okay? Let's use this guy right here. So that's like 1 over y plus 1, y minus 1 times dy. Let's do our partial fractions now. If you remember, we rewrite this as a over y plus 1 plus b over y minus 1 equals 1 over y plus 1, y minus 1. Okay? And then what you can do is multiply both sides by this least common denominator here, y plus 1, y minus 1, and simplify. That's going to lead to this, a times y minus 1 plus b times y plus 1 equals 1. There are a couple of approaches that people will teach with partial fractions following this step. One approach is to create a system of equations, so that's distribute the a, distribute the b, collect y terms and collect constant terms, and then set that equal to this guy on the right-hand side, or in other words, equate coefficients. That creates a system of equations that you can solve. It's a straightforward way to do it, but I have a preferred way. This is supposed to be an identity, meaning for all values of y that I can plug in on the left-hand side, these two things should be equal to each other. Notice if I plugged in a 1 for y, if I said y equals 1, this term goes to 0, and my right-hand term becomes, the second term becomes 2b. So I end up with 2b equals 1. Or if I divide both sides by 2, b equals 1/2. Okay, so if I plug in y equals 1, I get one of the two unknowns, b equals 1/2. If I plug in y equals negative 1, that makes this term go to 0, and I get negative 2a equals 1, or a equals negative 1/2. Okay, you'll get the same solutions if you do the other approach, equate coefficients and solve, but this tends to be faster. So notice what that means is if I come back over here, I'd have a negative 1/2 up here, a positive 1/2 up here, which I could plug in and rewrite this integral. Okay, but because I have a 1/2 or negative 1/2 showing up in either of these, I can also just pull that out of the integral entirely. So let's do a couple of steps in one here. I'm going to factor that 1/2 out, and then what I'm going to do is write what's left. So remember the b was the positive 1/2. Let's write that term first. 1 over y minus 1. This will become negative because a had a negative 1/2, or a was equal to negative 1/2. 1 over y plus 1 dy. Okay. Now notice I could do the same thing on my right-hand side because it was essentially the same expression, just in terms of x. I'm also going to have something that looks essentially the same, just with x's. 1 over x minus 1 minus 1 over x plus 1 dx. Okay? I'm going to do a couple of things in one here. Multiply both sides by 2 to cancel out that 1/2 term. And then notice the antiderivative here is going to be the natural log of y minus 1, absolute value, minus the natural log of the absolute value of y plus 1, which you can consolidate into this. Similar on the right-hand side, natural log of x minus 1 over x plus 1. Okay, and remember we only need the plus c to show up on one side. All right, now a quick note here. Because Calculus 2 is a prerequisite for this course, and because you should have worked through lots and lots of integrals like this, I may skip steps just to save time, because not only are we doing the integration, but we're doing more, right? So to save time on some of these examples, I didn't show, for example, the step in between here, which was that this integral becomes natural log of y minus 1 minus natural log of y plus 1, and then combine them. I just kind of jumped straight from here to here. So if that's a little confusing, try filling in the gaps on your own to make sure that you're tracking with me okay. All right, now normally we would start looking for an explicit solution at this point, but I'm not going to do that quite yet. Isolating the y is very difficult in this stage. So instead what I'm going to do is use my initial condition now. Once you've gotten it down to this point, you can really use the initial condition any time that you want. And remember, the whole point of that is to solve for c. I want to determine the value of this parameter. So what I'm going to do is plug in my initial condition. And my initial condition was y of 2 equals 2. I'm plugging a 2 in for both my x and my y here. So that becomes this, the natural log of the absolute value of 2 minus 1 over 2 plus 1 equals the natural log of the absolute value of 2 minus 1 over 2 plus 1 plus c. Now I don't really need to bother evaluating either of these explicitly, because I can see that these are the exact same thing, right? Natural log of this expression, natural log of the same expression over here. So subtracting those from both sides shows me that c is equal to 0. Okay? So now what do I get from that? Well, plugging c equals 0 into this expression, I'm thinking I'm going to run out of space here, I get the natural log of y minus 1 over y plus 1 equals the natural log of the absolute value of x minus 1 over x plus 1. Okay? I can do e to the power of both sides here, and that's going to drop the natural logs. I can actually also drop the absolute values. And why is that? Well, again, remember, we're looking for a part of the curve that the initial condition y of 2 equals 2 satisfies. And notice when I plugged in y of 2 equals 2 over here, what was actually inside these absolute values? Well, 2 minus 1 is 1, 2 plus 1 is 3, so I had a positive 1/3. The absolute value would have done nothing to that positive number. It's already positive, right? Now, because that's the case, and because we also define solutions to differential equations on intervals, if you looked at the domain of this function, the domain exists on a union of two intervals. I can only use one of those two intervals, and on the interval containing my initial condition up here, the 0.22, all of those inputs are going to be positive. So, all of these values in here are going to end up being positive. So the absolute value ends up not mattering, and I just get this. Y minus 1 over y plus 1 equals x minus 1 over x plus 1. Okay? Now, remember what our goal is here. Our goal is to find an explicit solution for y. And right now that looks pretty tricky. But what I'm going to do is try and cross-multiply these two rational expressions to see if things start to cancel out. So I'm going to come down here. I've got to use a new piece of paper because I ran out of space. If I cross-multiply y minus 1 times x plus 1, set that equal to y plus 1 times x minus 1. Let's see what we get. So multiplying this through, I get xy minus x plus y plus 1 equals xy minus y plus x minus 1. Is that right? Oh, sorry, this should be a minus 1 over here. Okay, the negative 1's cancel out, the xy's cancel out, and then what I have is a negative x plus y and a negative y plus x. Let me add the y over here and add the x over here. So I get 2y equals 2x, or just y equals x. That would be my solution to that differential equation, okay? Leaving it in implicit form technically is correct as well, but if we can get an explicit form for this function y, that's much more useful. And it's pretty clear that this is a much more desirable version of our solution than this. Okay? We have a couple more examples to do. I'm going to do that in the next video.